Welcome to the Explainer. Today, we're going to dig into the hidden physics that dictates how everything, from a simple rubber band to a massive skyscraper, actually holds together. So, what do a guitar string and a skyscraper have in common? I know, it sounds like a riddle, but the answer is actually pretty straightforward. They both respond to forces in ways we can predict. And, understanding that response is literally the key to engineering our entire world. So, let's start with the most basic idea. Okay, so at the most fundamental level, whenever you push on something, pull it, or twist it, you're causing what physicists call deformation. It's just any change in the shape or size of an object because you applied a force. Simple as that. To really wrap our heads around this, we're going to start with a really simple, familiar idea that is the foundation for everything else we're going to talk about. This is Hooke's law, and you've definitely seen it in action 1,000 times, even if you didn't know its name. For stuff like springs or metal wires, it's a super basic rule. The more you pull, the more it stretches. It's a nice, clean, straight line relationship. If you double the force, you get double the stretch. Now, that little k in the formula, that's the force constant. It's a number that tells you how stiff a specific object is. But, and this is a big but, k isn't just about the material. It also depends on the object's actual dimensions, its length and how thick it is. That's why the force constant for a thin little guitar string is tiny compared to a huge steel I-beam. So Hooke's law is great for the simple stuff. But what happens when you start to push things a little too far? Well, that's when the simple rules start to break down, and honestly, that's where things get really interesting. You see, there are two main types of deformation. On one side, you've got elastic deformation. Think of a rubber band. You stretch just a little bit. You let go, and it snaps right back to its original shape. It's temporary. But on the other side, you have plastic deformation. This is the point of no return. You've stretched it so far that you've permanently changed its internal structure. This graph shows us exactly where those boundaries are. First, you hit the limit of proportionality. That's the spot where that perfect, predictable line from Hooke's law stops being true. Go a little further and you hit the elastic limit. That is the true point of no return. Once you pass that, you're causing permanent plastic damage. And this leads us to a really big problem. Hooke's law kind of fails us here because its K value is tied to one specific object's dimensions. A thick copper beam and a thin copper wire are going to have totally different K values. We need a better, more universal way to talk about the strength of copper itself. To solve this, physicists came up with a kind of universal language. It's built on two really powerful concepts that let us compare pretty much any material, and it doesn't matter what its shape or size is. First up, we have stress. Instead of just looking at the total force pulling on something, stress looks at that force spread out over the area it's acting on. It gives you a much better sense of the internal pressure the material is actually feeling. And the other half of this puzzle is strain. Now, this isn't just about how many centimeters it's stretched. No, this is the proportional stretch, the percentage. Think about it. A 1 centimeter stretch in a tiny 10 centimeter wire is a huge amount of strain. But that same 1 centimeter stretch in a 100-meter long cable, it's practically nothing. And here is the absolute game changer. By using stress and strain, we're not talking about a specific wire or a specific beam anymore. We're talking about the fundamental properties of the material itself. We can finally compare the steel in a guitar string directly to the steel in a skyscraper. Okay, so now that we have this universal language of stress and strain, we can find the unique signature, the fingerprint really, that defines any material's stiffness. And here it is, the big one, Young's modulus. It's this single, incredibly powerful number that tells you how much material resists being stretched or squashed elastically. You can really think of it as a material's stiffness, DNA. For any given material, like steel or copper, this number is a constant. And just look at this comparison right here. Steel has a massive Young's modulus. It's through the roof. That's why it's so incredibly stiff and why we use it as the backbone for buildings. Copper is kind of in the middle, and then you've got rubber, way, way down at the other end with a very low Young's modulus, which is exactly why it's so easy to stretch. The beauty of this is just how elegant it looks on a graph. If you plot stress versus strain, the Young's modulus is simply the slope, the gradient of that initial straight line. A steeper slope means a stiffer material. It is that simple and that powerful. So, with all of this knowledge in our back pocket, we can now start to classify materials based on their unique personalities, how they actually behave when you put them under pressure. We can describe materials with a few key terms. Something is ductile if you can draw it out into long, thin wires, like copper. It's brittle if it just shatters without much warning. A strong material can handle a really high amount of stress before it breaks, while a tough material can absorb a whole lot of energy before it finally gives up. This table sums it all up perfectly. Glass is your classic brittle material, it just snaps. Copper is ductile, which of course is why we can make all our electrical wires from it. And a climbing rope, that is a perfect example of a tough material. It's designed to stretch and absorb that immense energy of a fall so it doesn't snap. Look, understanding these principles isn't just some academic exercise. It is the reason bridges stand up and planes can fly. But the next frontier, the really exciting part, is creating new composites and smart materials with combinations of these properties that we've only dreamed of. And that, right there, is where the future of engineering lies.